Hi there, welcome back to another video. In this video we're going to be taking a look at the proof that there are infinitely many prime numbers. Now, a few things to remember before we start this. Firstly, the definition of a prime number. A prime number is any number which has only 1 and itself as divisors. So 2, 3, 5 and 7 are prime numbers, but 10 is not a prime number, for example, because 2 times 5 is 10. Now, we're going to be taking a look at Euclid's proof, which is from around 300 BC, so I'll just write that down. And this is perhaps one of the most famous proofs in mathematics for a number of reasons. One, because of its significance, and it has far-reaching consequences. So the proof of this theorem actually allows us to do a lot of stuff in mathematics, which you'll learn later on. Okay? Also, the other reason it's quite famous is because a lot of people seem to have different ideas about how it was proved. So some people say it was proved directly, so I'll write that down. And some people will say that it's done using contradiction. So we've had a look at contradiction already on this channel when I proved that the square root of 2 was irrational. Yeah, we said to prove square root of 2 was irrational, we started by assuming it was rational. So I'm just going to write PBC. Now, as I was saying, there's a lot of debate in the maths community about if proof by contradiction is the correct method or if it was just proved directly. Now, what I'm going to do is prove it directly and then show how people are using contradiction to prove the same thing. Okay, before we start, a few useful things. A divides B, that's what this symbol means, so I'll just write that. A divides B if there exists an integer C such that B is equal to A times C. That's all that notation means. Right, and then something else which is going to be useful later. If A divides B and A divides C, then A divides B minus C, the difference between B and C. So I'm advising you to have a go at trying to prove this using the definition 1. Okay, so let's start with the proof. Right, so what we want to do first is consider a finite list of prime numbers. So let's call these P1 up to Pn. I'm going to write them in a set. So Pn is our biggest prime. What we're going to do is trying to show that there exists at least one prime not on this list. So we will show that there is a prime not on this list. So what will this do? Well, then as this is just any finite list, as this is any finite list, we are done. Because if there's some prime not in here, so if there's some prime not in this list, then this must mean that the list is incomplete, and so there are more primes out there. Then, because we can take this finite list of primes to be as big as we want, this will prove the statement that there's infinitely many. Now, where a lot of people get a bit confused is they start off by assuming that there's only a finite number of primes, and then they argue that contradiction solves it. Okay, so we've got everything we need now to be able to start, so let's do it. So we've got our list of primes, so let's consider this number. So consider, we're going to call it capital P, and it's the product of all these primes, and we're going to add 1 to it. Now let's have a look at this number. Okay, so what can we see about this number straight away? Well, firstly, it's bigger than any prime. So P is bigger than Pi for any I. That's all this means. So this thing P is bigger than any of our primes in our list. Now we have two cases to consider. So any integer, this is an integer. Any integer has two options. It can be prime or not prime. So if it's prime, that's p we're talking about, then it's a prime not on our list. So what have we done? We found a new prime not on our list. Okay? If it's not prime, then by something called the fundamental theorem of arithmetic, so I'm going to put that there, and if you want to learn more about this, then let me know and I can do a video on it. Then by the fundamental theorem of arithmetic, p has some prime divisor. Right, p has some prime divisor, let's call it q. Okay, and what this means is that q divides p. Remember our divide notation from earlier? Okay, so we're looking good. This case is done. So if p is prime, then it's a prime not on our list because it's bigger than any. Yeah, because it's bigger than any prime on our list. So that's good. So we're done in that case. Right, what about the case when it's not prime? Let's remind ourselves of what p is. Well, it's p1 times all the primes, and then you add 1 to the end. Now, because we have a finite list of primes, this q must be one of the primes in our list, i.e., so q is in our list of primes, p1 up to pn. And what does this tell us? This tells us that q divides the product, pn. So because q is one of the primes, it must divide this product because it's one of them. This means there's going to be no remainder when we divide. But now if we have a look at that number 2, so by number 2 up top, which I'll quickly scroll to, this said if a divides b and a divides c, then a divides b minus c. So we have, as q divides p and q divides this product, p1 to pn, then q divides their difference, p minus p1 pn. But remember, p is just this product add 1. So this tells us that q divides 1. Now this is impossible. Yeah? Q can't divide 1. Impossible. So what this says is that there exists some integer such that 1 equals q times c. And this just doesn't make sense because q is a prime number. This tells us that q was not on the original list. And so we're done. Remember, we wanted to prove that in any case there was a prime not on the list. Therefore it can be extended. Okay, now I'll quickly talk through about where people go slightly wrong in assuming this is a proof by contradiction. So, up here somewhere, they'd say, assume only finitely many. So let's say p1 to pn again. And then, so they've said, assume there's only a finite number of primes in total. Right, and then the working is the exact same. They get down to this point here, and they say, so this is impossible, hence our assumption must be false. Contradiction. Hence infinite primes. Basically, our proof is proving it by cases. We've considered this number, we've said what happens if it's prime, we've said what happens if it's not prime. We've shown that if we have any finite list of primes, there's always a prime that's not going to be on that list. Because we can take a list of primes to be arbitrarily long, i.e. it could have, many elements, this proves that there are infinitely many primes. What happens when they add this proof by contradiction bit, so I'll write this here, PBC, is that they've sort of wrapped the proof up in a shell, with the starting assumption, assume only finitely many primes, and the end, contradiction. Okay, so hopefully that makes sense. Right, let's quickly run through again, and hopefully everyone understands. So, to start, we consider a finite list of primes. Note we're not saying that this is all the primes. We're just saying take any list of primes. We want to show that there's a prime not on the list. As this is any finite list, then we'll show that there's always another prime number. Okay, we consider this product here. Right, it's the product of all the primes in our list plus 1. We can see that this product plus 1 is bigger than any prime number for any I. Okay, now we split it into the cases. If it is prime, then it's a prime not on our list because it's bigger than any prime. If it's not prime, then by this thing called the fundamental theorem of arithmetic, which again I can explain in another video, P has some prime divisor Q. Okay, the fundamental theorem of arithmetic basically says that any number that's bigger than 1 has some prime factorization. So it can be split down into a product of prime numbers. Right, so if P has some prime divisor, then it means Q divides P. But we also know that Q divides P1 to Pn. Right, where we're assuming that Q is on our list. Okay, if Q's not on our list, then we're done again. But if Q's on our list, then it must divide the product of those primes. And we arrive at this conclusion that Q has to divide 1, which is impossible. So this tells us that Q was not on the original list. And so we are done. Okay, thanks for watching. Any questions, do let me know. Stay tuned for the next video.